Okay, so here's our first problem in trying to write an equation for shear force and bending moment for this particular beam. So I've already kind of tipped you off a little bit and denoted that this is where we're going to cut the structure at some distance x. Now, like all of our problems with equilibrium, you're going to have to decide which free body you want to work, the left side or the right side. Now, I think the choice will be pretty clear. If you look at the left side, what does this look like? A triangle. We know how to handle a triangle. We know the area of a triangle. We know where the centroid is. The right-hand side would be a triangle and a rectangular. It would just be more work. And in addition to that, what is this distance if I work the right-hand side? 20 minus x. And you will find out that unless there's a huge advantage to doing that, this term, as you run through all your equations, will be a little more trouble to keep up with. So I think right now, the left side seems to be the best. Now, what's the downside of going to the left side? You got to find all these reactions. So there is a little bit extra work. But I'm going to do it that way today. So I'm going to start by drawing a free body diagram of the whole structure. And I'm going to, on the left-hand side, I'm going to apply positive shear and positive bending moment. Since we're writing equations for shear force and bending moment, I'm going to use shear force and bending moment as my unknowns. What's the concentrated equivalent load of this entire piece here? Area of a triangle. So it's going to be 1/2 base times height, so it looks like it's going to be 20, and it's going to be located 1/3 from the big end, or 2/3 from the small end. So 2/3 of 20 is 40/3. I'm going to leave it as a fraction right now. Okay? And that's it. So what are my reactions? Well, if I come here and sum moments about A, make sure we're in equilibrium. This moment with my sign convention for statics is positive or negative? Negative. This moment also creates, this force creates negative moment, so that's 20 kips times 40 thirds feet. So what is my moment? It's negative whatever that is. Whatever 800 divided by 3 is. 2.667? 266.7?
Yes.
Sorry. Mr. Story, you have a question?
Yes, sir. On point A, that's considered a fixed support, right?
Correct.
How come a fixed support doesn't have 3 unknowns at the moment?
Yeah, I probably should have included the axial component. We're going to find out it's 0 because there's no horizontal forces. Yeah.
It's not clear to me on that and why you're using the internal convention instead.
I'm not. I'm using the convention for shear force, bending moment, and axial force.
And why not the external statics convention on that end?
Because I don't want any. I'm going to end up writing an equation for shear force and bending moment. So if you just assume some moment and some force, you'd have to come back and figure out whether they're positive or negative shear force and bending moment anyway. So why not just assume them from the beginning? So what's my moment come out to be? Negative 266.7 kip feet. Now the negative means what? It means I assumed the wrong direction, but because I assumed positive bending moment sign convention, then I know it's a negative bending moment. I don't have to make any corrections or any adjustments. So when I write an equation for a bending moment, what should be the value when x is equal to 0? Minus 266.7. If my equation does not give me that, I have a mistake. Okay, now let's do the sum the forces in the y direction. I'll assume up is positive. So I start over here. My shear force is up. My load is down. And that's it. So it says shear is equal to 20 kips. So what is the shear force at A? Positive 20. So my shear equation evaluated at x equals 0 should give me 20. All right, so now let's go over here and let's draw the free body diagram at the cut. So I'm now going to draw the left-hand side of this structure. And remember, we're cutting it at some distance x. But I do know my reactions. What are they? Negative bending moment, which is in this direction, of 266.7, and that's kip feet. My point got lost. And the shear is positive, which is up, and that's equal to 20 kips. Okay? Now we have a distributed load. Now, for a given value of x, what is the intensity of that load? Basically, I have to go back here and write an equation for the load. Now, that's not hard, right? Because what kind of curve is that? Linear. It's a linear line. All you know is intercept and slope. What's the intercept when x is equal to 0? 0. What's the slope? Rise over run. So the rise over run is 2 divided by 20 is 1/10. So this should just be x over 10. And you can check it. When x is equal to 0, what should you get? 0, and that's right. When x is equal to 20, 20 over 10 is 2. So it seems to work. Any questions about that? So now the concentrated equivalent force, I'll just call it F. Let's calculate what F is. Now for a triangle, it's always 1/2 base. What's my base? X. What's my height? X over 10. So the force now becomes x squared over 20. And what is the distance here? I'll just call it D. So what is D? 1/3 the distance. The distance is x, so it's x over 3. So a little bit more work, but not that hard. The last thing I have to do on the free body diagram is then indicate positive shear force, positive bending moment. And that is a pretty complete free body diagram for the problem. If you get that far, the rest should just be follow your statics and let it come out the way it wants to come out. The great thing about these problems, too, is when we're done, you might be able to check it and see if it works out right.
Where did you get your 1/2 x from again?
1/2 x. Oh, well, the area of a triangle is 1/2 base times height. So let's sum moments at the cut. Make sure we're in equilibrium. I think we've done that a few times already. So don't get nervous, don't get upset, don't get worried. It's just summing the moments at the cut. You've done it before. So what is the moment here? This is a positive moment, M. This force creates positive moment about the cut. What is the force? X squared over 20. What is the distance? X over 3. This 20 kip force, positive or negative moments about the cut? Negative. 20 kips, what's the moment arm? X. Don't forget our moment out here at the end. Positive or negative moment using right-hand rule? Positive. Solve for M. when you do that, you'll see you have this equation. It's a function of x. So I'll just go ahead and say x moment is a function of x. I'll put it in brackets so I can put the units on the outside. So the first term is negative x cubed over 60. Second term is 20x. The last term is minus 266.7. And that would have the units of kip feet. So there's an equation for our moment. Is it correct?
Yes.
Well, we have two things we know. What is the moment when x is equal to 0? We already know what it is. It should be negative 266.7 kip feet. Plug in x equals 0 here, and what do you get?
Negative 266.7.
Check. Where else do you know the moment? Just by looking at it. What happens here at B? Is there any moment at B? Better not be. It's a free in. Nothing to restrain it. So that means the moment when x is equal to 20 should be equal to 0. Put an x equal 20 here. What do you get?
0.
Did you do it, or are you just saying that? Oh, you're doing a Rain Man. Good. Now see, that makes me feel good. I think that's a pretty good answer. It matches my endpoints. I like it. Now what do we do? Let's sum forces in the y direction. And that should tell us what? Something about shear. So going up here, I'm using positive or up as positive. So I look over here, shear is actually down. My force is down. My force is x squared over 20. The reaction force is up. That's it, right? So let's solve for the shear. So shear as a function of x looks like minus x squared over 20 plus 20, and that should be units of kips. Now, do I know something about the shear?
I have a question.
Yeah.
What, in your function, you have a negative. Where did the negative come from?
Which negative?
The
In the shear equation? This one?
no, the moment.
Which one?
Right there. In the, right
Well, I solved for m. So solving for m, all these terms went to the other side of the equations. They all changed signs. That tricky algebra. You know, balancing around the equal sign. Don't forget those things. My kids think it's magic. You mean if I add 3 to this side and add 3 to the other side, it doesn't change anything? No. But the numbers are all different. Still equal. Oh. So, that's the sort of thing I guess you never outgrow, right?
No.
I see a lot of heads going, yeah.
It still matches.
Okay, so I know the shear at x equals 0. It's equal to what? I solved for it. 20 kips. When I put x equal to 0, what do I get? Yeah. What do you think the shear at B is? Is there anything there capable of shear? No. So at x equal 20, I should get 0. If you put x equal 20, you get 0. All right. Lots of green checks. So there you go. There's your equations. Now, although I'm not going to prove it mathematically at this point, is there a relationship between these two equations? If you look carefully. Think about Math 1910. Huh?
Is that algebra?
That is not algebra. If you do something to the moment equation, you will get the shear equation. That's correct. If you take the derivative of the moment with respect to x, you get the shear.
Really?
Well, that's anecdotal right now. I have not proven this to be true. But let's just say as we move forward, it's true.
Really?
So that's another thing. That's another tool you have at your disposal, a resource. If you take the derivative of your moment equation and you do not get your shear equation, big trouble in Little China. So that means something is wrong. And since the shear equation is usually the simpler of the two to do, that probably is pointing to you that moment may be your problem. So you have a lot of ways to make sure that the shear and moment kind of correspond to one another and that they also match my end conditions. Mr. Abner.
If we feel that comfortable with our moment, can we just take the derivative?
You can, but you risk the problem of if your moment is incorrect, you have now incorrect shear. Whereas you can see the shear equation is usually pretty easy to do.
But if we get it
I
right,
suggest that you do the shear equation and then check this to make you feel good.
there's just so much
I'm not
going on.
encouraging you to shortcut the process. All right, any other questions?
Isn't that what we're here for?